Hello and welcome. Today we're talking about finding lines and planes subject to a given set of conditions. All right. So these are classic problems that show up often on exams. They are problems that I think most students find fairly fun and they're easy to do. They use dot products and cross products quite a bit. So let's talk about the first problem we're going to do. We're going to do two different problems. One, we're going to be given a line and a point, and the goal is to find a plane which embeds both. Okay. So the idea here is you have some line L and you have some point there, and you want to find some plane where both line and plane are inside the plane itself. Or sorry, the line and the point are inside the plane itself. So we'll say that this is going to be, we'll call this point W and this line L. Okay, we'll have W listed as a vector. Okay, all right. So the line, the specific example we'll give will be R of t. We'll put it in vector function form, which is going to be 1 to negative 1 times 2 times t plus some reference point. Maybe that'll be a point called x naught here, and that point will be 0, 0, 2. Okay. All right, and then we also have W, and that's going to be equal to, let's say, 3, 2, 1. Okay. Right, so how to find this plane? So the goal is to find an equation for the plane. Right, so the easiest way to do this is to set up and actually find, the idea here is that this vector here, we'll call it V. That vector points out from x naught. You can think of it as pointing out from x naught. And then we have another line, another vector we need to make. We're going to make another vector here and call that vector W. Okay, so that's going to go, it won't go to W, it's going to go from x naught to W. Okay. So we need to come up with that vector. We'll call this vector U. All right. So again, V is sitting right here, and U is sitting right there. Okay. And once we have that, the idea here is if we take now U and cross it with V, that should give us N, our normal vector. Of the plane. All right, so V is given, but U, that's going to be equal to W minus x naught. All right, let's put that together. That's going to be 3, 2, 1 minus 0, 0, 2, and that will give us 3, 2, and negative 1. All right, so the next thing we want to do is do that cross product. So we have to then do 3, 2, negative 1, and cross it with our vector V, which is 1, 2, negative 1, I, J, and K. So this is U cross V, and that will give us that normal vector. And the normal vector points up like that on the graph there, right? And it is orthogonal to both U and V. So there we go. Now we have to do this cross product. I always like circling these with different colors. So it takes the matrix minor on all rows and columns not related to I there. And it's going to be, this one is going to be 0. Cool. All right. And then, so that we got the first entry there. And now we have to try the next one. So we take J and take the rows and columns not related to j, and now do the cross multiplication trick. But this one, of course, we negate the whole thing. That's the whole idea. So we have a -3, and then we have a minus a -1 times 1. Okay. I'll worry about that arithmetic later. I just want to write it down. And then finally, I'll go to k, find that matrix minor, and I get 3 times 2 minus 2 times 1. And now, let's just do all the arithmetic to get this sorted. We have 0, and so that's -1. That'll become a +1, and that'll become a -2, and then that'll become a 2. All right, and then finally we have 6 minus 2. Of course, that's going to be a 4. All right, so that's my normal vector. Very nice. Okay, the final thing we need to do now is write out the plane equation. And that's going to be, the plane equation is the normal dotted with x, our vector of variables, minus x naught. And that will be our reference point, and set that equal to 0. Okay, so that's going to be 0, 2, 4, dotted with x, y, and z, minus, and then we're going to have to get our x naught thing down there and bring it down here, and that's going to be 0, 0, 2. All right, and that's going to be equal to 0, and we should have it here pretty soon. It's going to be 2 times y, 0 times x, plus 2 times y, plus 4 times z minus 2, and that's going to be equal to 0. So that can be our final answer. We could box that up. What's really important is that you see all these steps in order to get it done. I think this is a really great problem to do. Students usually really enjoy it because it involves lots of visualization and a lot of calculations that none of them are very hard, but you have to know how to orchestrate the whole thing together. All right, let's go on to another problem. All right, so this is problem 2. And this is given 2 planes. Find the intersecting line. Okay, obviously the planes, if they don't cross each other, there won't be an intersecting line, but we'll assume that the 2 planes do have an intersecting line. So let's talk about, we'll have x minus 2y plus z is equal to 3. And we also, so this we'll call this a plane 1. And then we'll also have this one, 2y minus z is equal to 0. All right, and that right here, this will be plane 2. All right, so plane 1 has a normal vector that's equal to 1, -2, 1. We'll call that n1. And plane 2 has a normal vector 0, 2, -1. Okay, cool. All right, so now what we want to do here is come up with an idea of how do we find the intersecting line. Well, it's actually pretty interesting here. So let's talk about plane 1. And I'm not trying to draw this to be accurate, but the idea is you can imagine a plane like this in space, and that there's some other plane right here in space, and they should intersect like that to form a line. All right. In order to get that, all we have to do is find one point, x naught, that's intersecting to both of them. Okay? And then we have to note that, of course, the normal vector, that'll be n1 right there. And we should have another normal vector there, n2. And if I were to cross both of those vectors to each other, that should yield a vector that's orthogonal to both. That could be our v that could form the direction of the line. All right, so that's how we're going to do it. So our v is actually going to be the cross of n1 crossed with n2. All right, so let's compute that. So we still haven't figured out what x naught is. We'll do that in a second, but let's first just wrap up this cross product calculation. I, j, and k. All right, and then we're going to have 1, -2, 1, and then 0, 2, -1. I always like to do this in color. We multiply that, we take the difference, and we're going to get 2 minus 2. That'll give us 0. Very nice. And now we go to J. We form the matrix minor like that. But we remember for this second one, we always want to negate it. So we're going to have 1 minus 1. That's going to equal -1 minus 0. Okay. Finally, we make the matrix minor there. We multiply there and then cross it with that one. And we're going to get just 2. Right, now I always like to just simplify my work. Cool. So this is going to be my v vector that is going to be the direction, the vector of the line. All right, the next step then is to actually solve for x naught. We got to find a point that is common to both planes. It's going to be one point along this line. It doesn't matter which one it is. We just have to find one. All right, to do that, we have to look at our plane equations up here. We have to solve both simultaneously. So we bring that down here. And notice that if we look at the second plane, plane 2, z is actually equal to 2y. All right, and now what I'm going to do is substitute that into the second plane, or the first plane equation. We're going to get x minus 2y plus 2y is equal to 3. Those actually cancel. That's kind of nice. And that leads us to x is equal to 3. So we got our first point, right? So that allows us then to figure out what the other points are. So it turns out if x is equal to 3, then we can plug that in. It's going to be minus 2y plus z is equal to 3. That, of course, implies that 2y is equal to z. We already knew that from before, but it turns out that these are both free to choose whichever you want for these. So in this particular case, what I can do is actually say that z is equal to 0, and then so is y equal to 0. Cool. All right, so from there, what we have now is x naught. We could figure out what x naught is. It's going to be 3, 0, 0. Right, so my line, this is my final answer. I can represent it by r of t is equal to 0, 1, 2 times t plus 3, 0, 0. All right, remember this is any point on the line that happens to satisfy both plane equations. Okay, you could have found a different point along the line. Any would be fine. All you have to do is find one. So there's always a little guessing that you can do here to do that. So here I'm going to box up my final answer. There we go. And of course with this is a parameterized equation. R then is any real number, and that makes the line stretch off to infinity in both directions. Okay. Well, I hope these two problems show you how just different examples of techniques of finding various lines or planes that satisfy some set of conditions. Typically, they involve some sort of geometry step where you have to incorporate some knowledge of and cross products and orthogonality, and you have to orchestrate your problem in such a way that you can then do all of your math clearly. Of course, you'll want to show all your work, all your arithmetic, and all of your reasoning behind this to develop a good answer to the problem. The answer is hardly the point on an exam. I'm really looking at how the work is coherent with what you get. All right. And of course, I want it to be correct as well, but it's really important that there's a logical flow through the thing from start to finish. Thank you very much.